improve industrial efficiency. I am Mary Benson from the Ameren, Illinois Acton Energy Program, and Bill Scales is the CEO of Scales Industrial Technology Incorporated, and he is an internationally recognized expert in compressed air systems. We also have Bob Baumgartner on the line to tell us a little bit about the Acton Energy Program a little bit later in the presentation. Some material from today's presentation was developed by Bill Scales for the Compressed Air Challenge, Best Practices for Compressed Air Systems. Now, real quick, I'm going to cover a couple of practical items before we get started. Know that the participants are muted, so we won't pick up on any background noise. And also want to let you know this today is being recorded, but as you can see, the participant names are hidden, so no one else can see who all is logged on. And this recorded online training event and handouts will be available later on today on the Education and Training page of the Acton Energy website. Also, if you have any questions, please feel free to enter them into the chat feature. Some of you already have used that today, letting us know that you could not hear, so I appreciate that. And so, yeah, please feel free if you have any questions, enter them into chat, and we will get those answered for you. And after this session, I'll be sending a survey, so please provide me with your feedback, and this session is going to last about 60 minutes. Now, to get started, I'd like to hear from you what city you're calling in from today so we can get a feel for where everybody's at. I am in Peoria this morning. We have someone from St. Louis, someone from Champaign, Illinois, Champaign, Knoxville, Tennessee, Illinois, Greenville, Peoria, Marcells, Illinois, Springfield, Illinois, St. Louis. Well, thank you all very much for joining us this morning from all over the state, and one from Tennessee. Okay, now, real quickly, before I turn this over to Bill, we are going to take a quick 3-question quiz to find out what you already know about compressed air. That poll for you now. And if you could please submit your responses, you'll have about a minute. Okay, so it looks like most of you have submitted your responses. I'm going to close down the poll here in a few seconds, and I will share the results with everyone so you can see what everyone answered. It looks like most people answered E, 25% for number 1, B for 2, and A for number 3. So I'm not going to give the correct answers right now because we're going to take this same quiz at the end and see how much you learned. So I'll go over the correct answers at that time. So now I'm going to introduce Bill Scales, and Bill is an internationally recognized expert in compressed air systems and has been involved in the air compressor industry since 1952 as a hands-on mechanic, engineer, author, and consultant. He has visited more than 5,000 facilities and audited or provided energy assessments and audits of over 800 mid-sized and large compressed air systems throughout the world. So thank you very much, Bill, for joining us. and I will turn everything over to you.
Well, thank you very much for doing this, Mary, and for inviting me. Mary, I'm going to ask if you could take control of the screen right now so that I can move ahead to the first slide.
Okay.
Mm-hmm. Well, obviously, no, compressed air is not free. Or is it obvious? Too many people treat it as if it's a free resource, and certainly not the primary thing that people should believe. And I think part of the quiz was to really determine that. Mary, can go on to the next slide, please.
Okay.
See from this that we have quite a few different things where compressed air is really losing most of the input power. The greatest portion of it, at least 80% of the input power, is going to heat. So we have a problem where only 20% is delivered compressed air. Very inefficient transformation of electrical energy into pneumatic power. We have a problem with that, and if we understand where it's going to heat, and if there's an opportunity to recover that heat, why, a great opportunity to really reduce our overall energy costs. You could possibly turn control over it to me. 10 to 15% the input power get point of use. The rest of it is going to other things. I mean, we're treating the air. We're doing all kinds. We're getting distribution pipe losses. We got miscellaneous losses that go on. With so many things that are problems for us in the compressed air system. So we're saying approximately 10 to 15%. We had systems where it's less than 10%. So we're constantly looking to reduce the consumption of compressed air and then getting a proportionate reduction in the input power to the compressor. When we evaluate the 10-year life cycle cost of an air compressor, and this was done quite a few years ago, and we did have it updated so that we were able to just make certain that we were still on the same page with all of these things. So we had some problems here with relative to are these pie charts still accurate? And we had them done again. I call the consultants who are actively involved in the compressed challenge, and while prices have changed, the ratio of these things haven't. You can see that over a life cycle cost, the great cost is the electricity. Cost, which too many times you'll find that the purchase is based on what the bottom line price is, and only 12% on a 10-year life cycle cost, and the maintenance is an additional 12% over the life of the compressor. Let's call it 10 years. So we can see that the opportunities really are on the electrical energy side. Versus other sources of energy, something that we look at. We've already covered the fact that it's as low as 10 to 15%. It's a very part of most plant operations. It was almost no manufacturing process that I've seen that doesn't require compressed air, and I've seen all types of operations, whether it's an oil refinery or something that converts alumina to bauxite, or a stamping plant, or whatever it is, tile mills. The savings of 20 to 30% are very possible. In some cases, savings exceeded 50%. And we have cases where a plant was running with a 350 horsepower air compressor, and just by changing the use of compressed air and using another source of power, that plant today is running with a 75 horsepower compressor that's only operating at about 80% of its put capacity. So they're operating at 60 horsepower when they were running 350 horsepower in the past. So things like this are possible. That's an unusual case that I just mentioned. At least it does indicate that it's possible. The cost to generate compressed air. That's been in almost all of the plants that I've been in and done audits. Not all. Many do know what the input power is, and they know what the output CFM is, cubic feet per minute. So as output over input is efficiency. For the system, we already know, as off in the pie chart, the energy cost exceeds any other cost. The other thing, note, annual cost will generally exceed the purchase price in the first year. Horsepower to capital cost is $40,000. 8 hours operation, the energy cost $5,900. We used 8 cents a kilowatt hour, but obviously if yours is less than that or more than that, you can ratio that number. Simple here. Regardless of what size compressor you have, you can list what the cost is, and of course at the bottom we've noted that again that's using 8 cents a kilowatt hour. If you want to approximate what the cost of your compressor is operating at full capacity, full load at the design pressure, 8 hours a year, for example, you see a 100 horsepower compressor. There's 110 brake horsepower. This means at the shaft, we actually need 10% above motor nameplate. And unusual. Rotary screw compressors today, almost all of them, they rate above nameplate horsepower, taking advantage of the 15% service factor, so 10% above motor nameplate. So all of these costs are based on being above motor nameplate, 10%. Now obviously if you're operating an exactly motor nameplate, that cost will be reduced approximately 10%. So now you have an idea of what your own compressor is costing you. Understanding all these little issues that we've suggested that a compressor can cost, it's a measurable asset. But of course, if you can't measure it, you can't manage it. Typical compressor system doesn't begin with the air compressors. You can see from this on the left-hand side of that there, you'll see that the compressors and the dryer are there, and we go into an air receiver. And then we go on the right-hand side of that drawing, where you're going to what is the demand side, the end uses are. And the supply side, as you see, what we're looking to do is to provide stable pressure and clean, dry, compressed air at the lowest cost. Doesn't mean that you provide overpressure or that you drop to a dew point that's far lower than what is actually needed. Pressure means higher cost. Dew point means higher cost. And of course, the demand side, we've included the distribution piping and any end-user receivers at the point of use. The goal is to minimize the wasted air, to use compressed air for anything that could be potentially inappropriate. And of course, maintaining the performance, including energy and reliability. Of course, you have to control and address both the supply and demand sides and make that management sustainable. The starting and the existing potential problems and opportunities are at every point in the system. This is not just about the air compressors, it's a complete system. And take a look at the air compressors again, and we've laid all the different components that are there, the dryer, the filter, the primary air receiver. That optional pressure flow controller is pressure reducing valve, pilot operated. Basically, that's what it is, and they're rather sophisticated so that you're maintaining the line pressure at a given point, regardless of what the pressure is upstream, which is on the supply side. That some applications, many times most plants want to stabilize their pressure and keep it plus minus 1 psi. They're able to do it with this pilot operated regulating valve, but would mean that they would operate at a higher pressure upstream of that, which you have to weigh the benefits and the cost to a cost justification. It is largest. It was identified as being the big opportunity that was identified in the late 1990s by the Department of Energy, and that compressed air challenge was formed. But people didn't realize it was so expensive to put in use compressed air. This lack of information has been a barrier, but there have been substantial improvements in the industry since that time, and some of the things that Ameren is doing today, as an example, is to better awareness across to the public. Is the biggest problem. people are aware of the cost very often, what we'll find is that the consumption will be reduced and the energy cost to produce that will be reduced. So we just have to have many people aware of what it's costing us and the mix of compressed air, of course. And the example earlier of the company that's now operating with a 75 horsepower that was operating at 350 horsepower. The final bullet is typically sold on the lowest first bid without regard to the cost of operation. And that we change the solar going back up. See if there's a risk to production. If you're going to reduce the pressure to 2 psi, production can really look at askance and say, now wait a minute, that's going to harm my production. Well, maybe it will and maybe it won't. So we want to make sure that we're coordinating with production before we do anything and telling them we're doing a test to see what happens. Low pressure will result, and we'll get that a little bit later, lower pressure will result in lower costs. You can measure it, you can't manage it. Baseline before implementing any changes is essential. Do I with the supply, demand, or distribution? Well, that's a good question. Let's get back to the first one. If you know, again, what W is, the input power, and your total kWh at a period of time, what hours your energy, then you'll begin to understand what exactly it's costing you. And you can say, okay, if I start to implement any change, what change resulted in savings? So baseline becomes important at your starting point. If you start to do simple changes, low-hanging fruit. The evaluation, you can do a system, and we're looking at the supply side, the end uses, the pressures, the air quality requirements. And in the lower right-hand corner, we're seeing a data logger. That's really recording the information that you may be monitoring or measuring, whether it's kW or whether it's CFM output or what consumption. We've got that data log. We normally look at energy, whether you do it weekly or monthly, and of course it might vary seasonally depending upon the season of the year and what the manufacturing loads are, and whether it's first shift or third shift. The pressure, the leak, very well to measure leak load if you're running 24/7. But in any event, on a down day, it's possible, of course. We just run an air compressor and nobody's using compressor in the plant. And flow will tell you basically leak load would be that sometimes there are variants to that, and you have to know your equipment to know some of the production is kept pressurized for various reasons, even though you're not producing anything. And at that point, while it may be considered a leak, it's non-productive use, you must keep the air on. And there are applications like that. Instrument air might be an application that I mentioned. Before making changes to the system, the question is why? Well, you know exactly what as a result of that change. So you take these measurements both before and after. The key points throughout the system, some people want to change the distribution piping because they think they have pressure drops at the end of the system, but it's not their piping that's the problem. It could be an end use where they have a clogged filter. Rising pressure at the end use combined with a corresponding reduction in compressor discharge pressures. So if you could find that at an end use, that you were operating at an elevated pressure at the discharge of the air compressor because this end use had a large pressure drop in some of the components, if you reduce that pressure drop at the end use, could you reduce the pressure charge at the compressor and reduce your energy input cost accordingly? They occur just prior to the point of use. We find that many of our problems are right there, right at the end use. They're not in any place else. We call it the dirt 30, the last 30 feet of piping. Come into the end use is where we find problems, whether it's a filter regulator lubricator, filter being a prime example of another, or some of the internal piping that's there at a particular process, or incoming distribution of hoses or tubing or whatever. Which tasks can most easily be done? Start with the easy ones. That baselining is one at a time, measure the effects of each and see what the effect is on reducing your cost as you implement each individual initiative. Air at the lowest possible pressure. That rule of thumb, and the rule of thumb on a rotary screw compressor and some of the reciprocating compressors, not necessarily on centrifugals, that we can discuss at a different time, but if you can reduce the discharge pressure at the compressor to PSI, use the input power 1%. See if you can reduce the pressure in the system by PSI, you get almost a 1% reduction in the consumption of compressed air to everyone using full line pressure. Component demand. Notice that this pi is really that 20% of the total input power that's converted into pneumatic power. And of that 20%, only production uses 50%. The lease account for anywhere from 10 to 20%. I'd say in today's world, because of everything that's been written, probably 10% or less in most of the plants I've seen most recently, although there are still some that go above 20%. Inappropriate use is 15 to 25%. That we can eliminate or replace compressed air with some other source of power. Artificial demand means the elevated pressure you have put into the system because some process or some component requires that elevated pressure, so you have the entire system operating at a higher pressure, and therefore everyone who's in that full pressure consuming more compressed air than they would at the low pressure. That's called artificial demand. The point of use issues. Reduce the highest point of use pressure requirements. Determine the actual air quality requirements. Treat air appropriately. This means if you have a dryer that's giving you a minus 40 degree dew point and you only need it for one purpose in the entire plant, maybe it's an outside piping system, doesn't mean that the entire plant should be getting minus 40 degree as the pressure dew point, when a 35 degree dew point might be adequate. The air requirements and address high volume intermittent application by an air receiver. If the plant pressure is used quite a intermittently, once or twice during the day, maybe just adding a storage receiver at that point of use would eliminate the reduction in pressure that the entire system is seeing. Point of use requirements, especially those that require high pressure or have a high volume requirement for an intermittent application. Production personnel. When too much of production says no, we don't want to have anything change. Examples where gauges were changed and somebody, then because we knew that the old gauges were reading, they were inaccurate, they were reading higher pressure in the system downstream of the system that we're actually getting in the air compressor room. So those gauges downstream were replaced, and production complained that we had reduced their pressure in the system, when in fact we hadn't. We had just used the gauges. Keep them fully informed. Let all management know what the dollar savings are. That's really where Matt has a key interest, and sometimes the chief financial officer can be the greatest partner in order to improve the compressed air system. And sustainable quality and reliability is the goal. This rule of thumb I just told you about, one input power to the compressor. the inappropriate uses. You fix all your leaks, not just identify them, fix them. Good maintenance procedures throughout. For compressor controls is highlighted here. If we do all of these things to reduce their consumption, and it doesn't result in a purported reduction in the input power and the total energy consumed, then we haven't helped ourselves to the point that we can. It's possible to reduce air consumption 10% and get only a 3% reduction in the input power, depending upon the type of controls you have on the compressor. So make sure that, to the extent possible, the controls are always readjusted every time that you have any kind of a change. You may want to call in your compressor supplier, or it's possible you can do it yourself. Adequate storage, meaning the air receivers, as we stated a few moments ago, especially for high-volume intermittent applications. There are other methods as well. Leaks. I've probably seen magazine articles written about leaks, and some of the rules of thumb: low pressure, less leak flow. Leaks minimize the supply pressure. Unregulated end uses will more air when pressure increases. This tabular form, the purpose of it is to show that at the pressure, for instance, if you go to 125 psig, 126 CFM. Now, perfect orifice, very things are perfect in life, and most of the leaks do not occur in a perfect orifice. They occur in so many different shapes, but a leak equivalent to a quarter-inch orifice would consume 120 CFM. Yet we drop that pressure to 100 psi. The same orifice consumes only 104 CFM. Here's at 90 is 95, and at 80, 85 CFM. By reducing the pressure in the system, the air compressors don't know whether they're feeding a series or whole many orifices, or it's feeding all the process that requires compressed air. So reducing the pressure to that system, everybody using full compressed air, you'll find that's the reduction that we're able to get. If you can reduce from 100 down to just 90, you really reduce the by about 9%. That's cost at 8 cents per kilowatt hour. They told me they $13,411 is more than your weekly pay, but I'm not so sure of that. Did you laugh because it isn't?
I don't think so.
You don't think so? Okay. If you want to cut costs, you've got to implement a leak remediation program. It's not something you do once and it's over. That's the end of it. It's ongoing. And production will always tell us where we have leaks, or maybe they're responsible for fixing their own leaks. But is that their main for what they're supposed to be doing? And sometimes it isn't. It's not the priority. Again, the awareness of costs is an important step. In leaks means that somebody has taken a piece of hose or a piece of tubing and put it on a conveyor line, as an example, just to help move that product along when there was nothing wrong with the conveyor line when it was new, but something's wrong, something's changed, so they use the air as an assist. That's an intentional leak. And then when the conveyor line stops, does the air stop flowing? Sometimes it doesn't. The compressed air continues to flow even though no production is taking place. The leakage rate. This we talked about. Calvings of reduced compressed air consumption. If your compressors are not capable of doing that, sometimes we have centrifugal compressors where any excess capacity is blown off to the roof, so you can eliminate all the leaks and you haven't reduced your energy, because what's happening is all that reduction in consumption in compressed air only resulted in a centrifugal compressor blowing more air off to the atmosphere than it had been doing before. So I want to make sure the compressors are controlled properly. just things that we wish to continue to reinforce. At the end use, there are leaks sometimes on the supply side, right in the air compressor room. We've found some plants where it's really been significant, but most leaks are at the end use. Again, maintain system pressure lowest possible levels, down to less than 5% of the system flow. It's not a possible thing. We've seen it in many plants, especially in the last 5 to 10 years. Potential inappropriate uses. A series of compressors, item number 4. Run part load. Usually at part load, they're relatively inefficient. And what we want to do, and really the goal, turn on unneeded air compressors. So you have 1, 2, or 3 compressors running fully at full load, full output capacity. Only one should be trimming. And that one should be trimming should have good part load characteristics to reduce your energy costs. The supply side, again, everything on the left side of that drawing is the supply side. Compressors, the filter, the air receiver, including primary receiver, and a pressure flow controller if it's present. And that's storage and air treatment, cleanable air, pressure, appropriate pressure in a cost-effective manner. We're looking at that high volume intermittent use as a worst case scenario as an example. Centrifugal and rotary compressors were better suited for continuous base load type of service, but we've improved part load efficiencies significantly in the last 5 to 10 years. Reciprocating compressors, for those who have them, are better suited to swings and load. You can shut them off, unload them, and they've operated a very low part load cost. So you're starting off with 100 psig in the compressor discharge into the air receiver, and you may wind up with 95 psi going out into the system. I guess spoke earlier about the one-angle application where you need air, perhaps outside the plant someplace for instrumentation, or maybe have a process outside, and that's the only place where you would need a dew point that's sub-zero or minus 40 degrees. Dry the entire plant there to minus 40. The most maintenance mistakes we find, again, you see that the first one is the end use, right end use. When we're not maintaining primary filters, we're all talking about leakage downstream of that at the process. And of course, condensate trap maintenance issues are avoided. People take care of the air compressors. The automatic drain trap is working, but really be cleaned and maintained. Poor ventilation in the air compressor room will cause problems with, motor tripping out, compressor tripping out on high temperature sometimes, not performing lubricant analysis, and not performing leak management. So 1 and 6, closely related. We've almost gone full circle with that, because again, most of the leaks are at the end use. Enforcing the fact that we only want completing fully loaded and with only one trimming. And prop-sized air receivers are part of the overall compressed air system control strategy. There are systems we've seen where they have no receivers. I was at a plant last week where that was true. In 2 systems, one of them, they're on opposite sides of the plant. One of them had more than adequate receiver capacity. The other one, where they had where other compressors running, had no receiver at all. That centrifugal compressor that I talked about, if you notice that what happens is in this centrifugal compressor, if you follow the green line down, you'll see that the demand is dropping in FM. That's along the horizontal axis. I think they call it the abscissa. What happens is that you'll get on the orange line, you'll find that there's a point at which it bends off to the left and it's horizontal. But even if you're operating at 40% of design capacity of the compressor, you'd be consuming with an inlet butterfly valve about 80% of the full load power. Because that 80% of design CFM, all it's doing is blowing off excess air to the atmosphere. And if you were controlled with a butterfly, an inlet guide vane, which is the inlet butterfly valve, you'll see that maybe you're able to get a better turn down and get on to start blow off at 70%. But then if you're operating at 30% of the capacity of the compressor, you'd still be consuming 70% of what load power would be. So you had a 1,000 horsepower compressor consuming 700 horsepower worth, for only getting 300 horsepower worth of output air into the system. So this is an example on a centrifugal compressor of why we wish to avoid what we call blow-off, which is the area in that horizontal line, butterfly valve, and the capacity modulation, which is showing the blow-off points between both the inlet butterfly and the inlet guide vane operation. Compressor started in a preset order, operating under pressure. As pressure fell, they would just start adding more air compressors, but it presented some complex problems, and they really identified, and things have changed in the past few years. We talked about compressors running a part load, and we've been in plants where they ran a 100 horsepower air compressor completely loaded, just in case one of the compressors went down. We had to take care of that, and this is that 800 horsepower. That 8 kilowatt hour, it's $60,000 a year. Plus maintenance on it, of course. We were able to monitor and control all the supply side components in the system, and win the data to enhance maintenance functions, minimize all the costs of operation. A system interface with all brands and types of air compressors. Doesn't matter whether you have reciprocating, rotary screw centrifugals, and it doesn't matter who the manufacturer is. It can coordinate all of those functions to operate at the lowest in power for any volume of compressed air consumption. It can also coordinate operation of satellite compressor rooms, different buildings, and even monitor and control other utilities, whether it's chillers or HVAC or humidity, all things, boilers, chillers. Reliable multiple compressed air system at a sustainable lowest energy cost. The word sustainable is very important in dealing with these. W. Man. You can't manage it. I think I've read that before. Say to you, different plant with the kW per CFM, CFM per kW, 5.4 was close on weekdays, and on some weekends it was always 1.0. It's kept the compressors running, and the compressors were not controlled properly. And on the weekend, when they had reduced air demand, the compressor did not react to that reduced air demand. That's in the same plant. status on some of the different controls that are out there. This happens to be a scales control panel. It doesn't matter, it can be anybody. There's quite a few different companies there. And it gives you the status of each of the individual compressors, what the dew point is that they're getting, which compressor are running, what the KW is, and what the flow is in SCFM, what the pressure and the dew point, and the SCFM per KW in the lower right-hand corner. You'll see what that was. So they have that on a continuous basis. They're able to monitor it. It gives you the hourly plant demand and the trends for various different jet mills in this particular case that within the plant. And they have for instrument air and also what their production process was. So you've got the low rate of these. Also, you can get dollars that amount for that as well very easily. Use the systems approach. We're not looking at individual components. We're looking at the total system. The demand dynamic, they're changing most of the time. Inner systems may not change too much, but most of the process and manufacturing demands do change. So we want to use the controls, the storage, and demand management so that the system is always meeting peak requirements and operating at peak performance at the lowest input power. Operate efficiently during low demand periods to result in a high performance compressed system. That's what we're looking for. This, of course, savings and production benefits, absolutely. And it's awareness that counts. Uses. I'll walk into the compressor room to get an idea of what's happening. Stay there for a while. Watch and monitor for a little bit. I try to get there for all three shifts if I can. Then I spend a lot of time out at the end uses. We talk about where now, and then you find out where you're heading as you continue to implement savings initiatives. This can be controlled, maintained, time deal, be maintained, and constantly monitoring CFM that's being consumed and the total KW and KWH. We'll know if you're maintaining it. Implementing is bold because it's a key word. It's do, not what you plan. That's important.
So much, Bill, for presenting that information about how to optimize compressed air systems. It's very interesting, and you can really save a lot of energy by repairing those leaks. So I appreciate that. And Bill is going to stay on the line with us for a couple minutes to answer any questions you may have. So please, if you do have any questions, type those into chat. And now I'm going to introduce Bob Baumgartner, who is an Industrial Energy Efficiency Manager with SAIC, which is an Ameren, Illinois Acton Energy partner. And Bob is going to tell us a little bit about the Acton Energy program and the cash incentives that it provides for compressed air projects. So welcome, Bob.
Thanks, Mary. First of all, I'd like to thank Bill Scales. Acton Energy truly appreciates Bill sharing his vast knowledge of compressed air experience with the Illinois customers. So thanks, Bill, for your time today. My job here is quick. It won't take much of your time, but I'm a commercial for Acton Energy at this point. This slide you see in front of you lists all of the incentive-based energy efficiency opportunities with Acton Energy. And really today, what we're focused on under the electric category, the compressed air. And Bill has done an excellent job of showing opportunities to save energy and to save money with compressed systems. And Acton Energy offers basically three types of programs, if you will, in the compressed air area. A leak survey and repair program, which is very simply focused on leak repair. A little more comprehensive than that is our retro-commissioning program, which involves more of a study of your system, as Bill mentioned, the demand and supply side, takes a close look at both sides, and we'll produce a final report, which is very detailed, and will give the customer a very good idea of where their compressed air system is as far as status and possibilities for energy savings. And that focuses mostly on 1-year simple payback types of items. Finally, we have our custom program, which can be far with a 7-year payback items, more typically capital equipment if you're going to be installing new compressors or storage tanks or things like that. So again, my name is Bob Baumgartner. I am the lead for the compressed air program. If you have any questions at all, or if you're curious, or if you want more information, feel free to contact me. I think my name on the applications and my contact information. I'll send it out to anyone at Acton Energy, and it will get to me, and I can be happy to work with you individually on your systems and facilities and to help optimize your compressed air systems. So, thanks.
Thank you very much, Bob, for sharing that information. And you can learn more on our website, so please visit. Now, real quickly, we'll get to a couple of your questions. I'm going to ask you to complete this quiz once again and see what you learned during the presentation today. So you'll have about a minute, and then submit answers. Looks like most of you have finished and submitted your answers, so I'm going to close the poll down here in a few seconds. 3, 2, 1, and I'm going to close the poll. And I will share the results with everyone. For number 1, the correct answer is there are actions you can take to save more than 20% of your cost of compressed air. So the D, 20%. The statement that is true for number 2 is D, compressed air systems that waste air also frequently have reliability problems that affect production. And 3 is true, compressed air is often the biggest end use of electricity in a plant. So that is very interesting. So I'm sharing those results with you there, so you should be able to see what everybody responded. Now, we have a couple of questions here, so I will those, and Bill can answer these for us. We have one question here that asks about retrofitting compressors with VFDs after resolving the other supply and demand side issues. Can you address that, Bill?
Yeah, many of the rotary screw compressors are, well, say many, some of the rotary screw compressors are candidates to be retrofitted. The things you have to look out for is we don't want to get the speed too low because then you have problems with a lot of slippage and leakage. And at the same time, of course, the motor should be inverter duty. We have problems with constant speed compressors. They have one speed at which they're most efficient. All screw compressors have an optimum tip speed, which means the speed at which the tip is operating at. So we're primarily about rotary screw compressors. That tip speed is 27 meters per second. If you go above that, it's like a bell-shaped curve. You go above that, your friction losses go high. You go below that, and what happens, you get a lot of slippage of the high-pressure air slipping back towards lower pressure. So you've got maybe a turn down that might be limited, as on today's compressor supplied by the manufacturers might have a turn down that'll get you down to 20 or 25% of the maximum speed. Now, there are compressors that are out there that are fixed speed compressors that can get down to 25% of the flow to operating RPM and still be relatively efficient. To know which compressor they are they candidates. When we've been presented with that opportunity, we usually find that only half of them really are good candidates, but they are out there, and those can be, should be. That was the question.
Very much, Bill. Now, another question. How often do you recommend a full system leak survey with ultrasound?
Plant is very quiet. I don't know that you need the ultrasound, but if the plant is relatively noisy, most manufacturing plants are, it really depends on the plant. There are plants that do it quarterly, some do it semi-annually. I would do it semi-annually. So that is answering the question. I don't know. However, I don't think there's a definitive answer to that. The reason I said if the plant is relatively quiet, if you walk along, you can normally hear in a quiet plant a significant leak. If you can hear it, fix it. An example that we use is that can be felt and heard, or let's put it that way, if you can hear it, and it's probably going to cost you somewhere around $1,200 a year in leakage if you just hear it as you're walking through a quiet plant. The thing that be most attuned to is make sure you fix the significant leaks immediately. If you have to take your ultrasonic leak detector and get right up next to tubing fitting in order to find out where it's leaking, it's worth the time right then and there to fix it. But zero leakage is always the goal. Whether you'll get there or not is another story. To answer the question?
Okay. I believe that does. Good. And if anybody has a follow-up question, you can type that into chat. We do have one more question right now. Should rotary screw air ends be checked for performance periodically, or do they normally fail at close to initial performance?
Lubricated rotary screw compressors normally retain their initial performance until the bearings go bad. You have to replace it. It doesn't mean that they always will, but if maintenance has been good, you're going to find that your performance has been there. The reason I mention maintenance, because if it's a lubricated rotary screw compressor and you're not maintaining it properly, the oil separator will get clogged a little bit, so you're compressing a higher discharge pressure and therefore a higher input power. The screws themselves, the way they're made, is that they'll normally retain their efficiency at the design performance throughout the life of the machine. The life of the compressor may vary with different manufacturers or different tolerances on a given product. However, they normally are right there. There's one comment I wanted to make. It's that while 20% is normally what we've seen as being the cost reductions that in doing it, 25% and more are very often what we're seeing when we've done audits. So the people who answered 20% or 25% are both correct. That first question, Mary, I just wanted to put that. However, getting back to the rotary screw compressor, hopefully that has answered that question.
Thank you very much. I don't have other questions right now, so if anybody has any final questions, please type those into chat, and I'm going to take this opportunity to tell you about a couple of upcoming Acton Energy training events. On January 11th at 8:30, we'll have David Gibson, a senior technical advisor with SAIC, presenting variable frequency drives, energy efficiency opportunities. And then on January 25th at 8:30, we'll have Don Fournier from the Smart Energy Design Assistance Center presenting on Do-It-Yourself Energy Audits. So please join us for those. I do not see any other questions at this time. So once again, I would like to thank Bill very much for sharing his expertise today, and thank you all for joining us from all around the state. And If you have any more questions, then this concludes today's webinar. Thank you very much for joining us, and have a great day.
Mary, thank you, Bob.